Morning, everyone. My name is Chris Miller. I'm a postdoc at Caltech. I'll be co-presenting this session today with Mike Oskin, where we'll talk about the role of remote sensing in earthquake mapping response. So the aim of this talk is to discuss the use of geodetic imaging data sets that are used by field geologists for guiding and documenting surface rupturing events. In this presentation, I'll start out and talk about data products made available for rapid response to field geologists in the first hours to days following an event. And then Mike will follow up and discuss data sets that are either collected in the field or which take longer to acquire and process, and therefore typically used for science research as opposed to rapid event response. So here we'll focus on geodetic imaging data sets, and these are really imaging techniques like INSAR or optical image correlation or lidar differencing that are used or that are made rapidly available. And so I won't cover point-based measurements like GPS or creep meters. So in this talk, we'll cover the different types of geodetic imaging data sets, their limitations, how they're used during field response, as well as how field surveying can help fill in some data gaps in regions that are not well resolved by these remote sensing data sets. So in this talk, I'll mostly discuss INSAR and optical image correlation, since these are the techniques that are most readily available to field geologists for rapid response. So INSAR is a technique that measures surface deformation with millimeter precision. It does this by estimating the difference in the phase of the radar wave between two passes, shown here. So if a point on the ground moves and the spacecraft is in a similar position for the second pass, the phase difference is between the two radar pulses is proportional to the ground deformation between the passes in the line of sight direction. And so with INSAR, you can only get an estimate of the amount of surface displacement in the direction that the satellite is looking. From the RAP data shown here, this is the RAP interferogram, you can then unwrap this, which is an additional step to get a continuous geophysical estimate of surface deformation. One issue with this is that with INSAR, it typically either decorrelates or the unwrapping is unreliable in the near field. And this decorrelation typically happens because it's undersampling regions of high phase gradients. And so this is where optical image correlation comes in. And this is really a complementary technique to INSAR because it really works well in the near field where displacement motion is largest and where INSAR typically decorrelates. And so typical pixel tracking algorithms work by taking a sliding window from before and after image, and then tries to match that distribution of pixels in the corresponding post-event image using either a statistical or phase correlation technique. So in this example here, the image correlation technique spits out the motion in the east-west and north-south directions. Okay, so why has there been a real uptick in the use or interest of geodetic imaging data sets for field mapping response? So the reason, one of the reasons comes down to ESA's Sentinel 1A and 1B radar satellites. And these are two satellites that provide very short revisit times on the order of 6 to 12 days. They have very low data latency, which means that it's only a few hours after the images are acquired that you can then access them. They're free and easily accessible. The processing is also free and open source for the most part. And then the other reason is the optical data. On the optical data side, there's an increasing number of satellites that are being launched. Planet Labs is one good example, which is a large number of shoebox size constellation of shoebox size satellites that provide very short revisit times on the order of hours, less than a day. They also have very low data latency. They're somewhat accessible. If you have an NSF or NASA grant, you can request access for those data sets. And there's also obviously lots of other optical satellites that can be used too. And so with the launch of NISAR next year, which is another SAR satellite, it's very likely that you will go into the field with some sort of co-seismic geodetic imaging data set, which may help guide your field mapping response. And so here's an example of most of the optical and radar products that could be produced and that you might use in the field. Some of these data sets weren't made available during the Ridgecrest earthquake that happened in 2019, but certainly in the future they could be, as most of the processing becomes increasingly automated and moves to the cloud. So in the future, it's likely you'll start to see more of these products coming out much faster. So I won't go into all of these, but some of the ones I'll highlight are the radar phase gradient maps and the optical strain maps. So the way that the radar phase gradient maps work, here's an example shown for the Ridgecrest event, which worked really well at picking out smaller fractures. Is that this technique calculates the gradient of the interferogram. And so this is advantageous because it avoids the step of unwrapping the phase, meaning the data aren't subject to these unwrapping errors. And so you don't produce these spurious artificial faults from unwrapping itself. You can think of these phase gradient maps as measuring a component of strain, as it's simply a spatial derivative of surface motion in the line of sight direction. And so because you're taking the gradient, this also highlights these small spatial details. So these phase gradient maps are really helpful for showing regions of strain localization of smaller fractures further away from the primary fault rupture. So on the optical side, you can also strain maps are now a popular technique, which is also just another kind of gradient mapping technique. And this is now possible because the images, the optical satellite images are being acquired at increasingly higher resolution. And so from these strain maps, you can look at things like, you can resolve the magnitude of shear, magnitude of strain, rotations, fault perpendicular contraction or extension, which is typically difficult to measure in the field. And so this can really help illuminate and understand regions of very complex fault kinematics, which in the field could be useful if you're time constrained and don't have time to fully map or understand the complex kinematics of a region. These types of strain maps could be quite useful. Okay, so lastly, I'd like to end on the topic of, given the limitations of the data sets I just presented, what can field survey observations bring that this geodetic imaging technique simply cannot? So first off, field surveying can provide very high temporal and rapid sampling of fault offsets. This is a good example along the 2014 Napa earthquake, where after only one day, about 5 centimeters of afterslip was observed when remeasuring the site. Also, field observations can provide very critical information in being able to separate the on and off fault deformation. And so like I showed here, the optical strain or displacement maps have a difficult time in separating fractures that are very closely spaced together or have low amounts of displacement. And so field observations can help with this problem. And so the take-home message here, I hope you get from this presentation, is that there's a range of different geodetic imaging data sets and products that are available within hours to days following an event. They each have their own limitations, which is important to be wary of when you're using them in the field, but they can be useful to help guide your initial mapping response. With that, I'll leave it there. Thank you.